All right, so we're going to start now adding to our toolkit, if you will, of familiar probability distributions, things that are in the continuous realm. We've got quite a few discrete cases already. You're looking at like the binomial, negative binomial, hypergeometric, Poisson, some other ones. They're all discrete. So what we're going to do now is we're going to switch gears for a while, and we're going to start talking about continuous probability distributions. So just remember that the mechanics here are a little bit different, that we're going to be using integration versus summation, for example. We're going to start with the continuous uniform distribution. This is probably one of the simplest distributions. It has a flat probability function. Okay, so let's go ahead and just start with the definition here, and then we'll take a look at the distribution itself. The density function of the continuous uniform random variable, continuous, so CTS, continuous uniform random variable, capital X, on the closed interval from A to B is density function here, f of x. This goes from A to parameters, go from A to B. This is equal to 1 over B minus A when x is between A and B, and 0 elsewhere. And 0 elsewhere. All right. So A and B are constants that are given to you. So this function is equal to 1 over B minus A. That's just equal to some constant over that interval, right? So let's do this in orange here. So for example, the continuous uniform distribution on the interval from, say, 0 to 3, on the interval from 0 to 3 then, would be f of x equals 1 over 3 minus 0, would just be 1/3. Sorry, what do I want to do here? That is 1/3. That is true. Yeah, sure, that's fine. That's fine. And then graphically, right, so graphically here, we have x, f of x. So from 0 to 3, so there's 1, 2, 3, it takes on a height of 1/3. So let's see, if this is 1, maybe here's a half. So then a third is about right here, roughly. Okay, so this is going to be, essentially takes on this height. Right there, and that is essentially our distribution. Notice the area in here is equal to what? Well, we don't need to integrate. Certainly we can integrate, but that's just a rectangle, right? The area there is height third, base 3, area is equal to 1, which is good because that's what we expect when we have a valid probability density function. So it's pretty simple to work with. And in fact, when it comes to computing probabilities, because this is it's a flat curve, right? It's a flat curve. Actually, this is our density curve goes to here. It's just this here to here, essentially. And this should really just be dashed just to kind of indicate that that's ending there. And then 0 elsewhere, so open dots, kind of like that. We're looking at just a rectangle. So basically you just need the height, or whatever the height of the density is, and then the length or the base of it, and we can calculate our probabilities there. But we can always integrate, and maybe we'll do that just to get back into the feel of working with continuous distributions. Because certainly in other continuous distributions, they're not quite this simple. Let's dive into just an example working with this. let's say that the random variable x has a uniform distribution, on the interval from 0 to 4. So part A, let's go ahead and write out what is the probability density function, what is the PDF, and part B, what is the probability that x is greater than or equal to 3. X has a uniform distribution on the interval from 0 to 4. What is the probability density function? Excuse me. So we just want to go ahead for part A here. Just want to go ahead and write out the probability density function, f of x. This is equal to 1 over b minus a. So in this case, it's 1 over 4 minus 0, or simply 1/4. And we should include the bounds here, f of x equal to 1/4 for x between 0 and 4. Everything else, it's 0. Let's not forget that. 1/4 between 0 and 4. Those bounds are really useful, obviously, well, and important, because when you look at part B, asking about the probability that x is greater than or equal to 3, technically speaking, right, if we're going to be complete, we would integrate from 3 to infinity our density function, right? Integrate from 3 to infinity, but we know that our density is 0 for anything after the upper bound here, which is 4. So in this case, we just need to integrate from 3 to 4, 1/4 dx, 1/4 dx. And so if we want to do the calculus here, that's 1/4 x evaluated from 3 to 4. So we have 1/4 times 4 minus 3, which is 1. So 1/4 times a 1 is 1/4, or 25%. All right, so we have that. Again, once we identify what the length of the interval is here, right, in the continuous distribution, you could look at this as saying it is going to have a base of 1, because you go from 3 to 4, and a height of 1/4, right? Think about the picture here. We're going to go from 3 to 4, and the height is 1/4. So we really just want the area under this curve here, which is just a rectangle. 1/4 times 1 also equals 1/4. Same thing. Okay. I'm going to add a part C to this. Let me add a part C here. Let's talk about maybe probability that x is, let's say, greater than or equal to 3, given x is greater than 2. Given that x is greater than 2. Let me just add that here real quick. So here we go for part C. Given that x is greater than 2. There's a couple ways you can go about doing this. One of them is just to use the strict definition of conditional probability, right? So what does this mean in just terms of a conditional probability? This is the probability of the intersection divided by the probability of the given. So this is the probability of the intersection of both events, x greater than or equal to 3, and x greater than 2, divided by the probability that x is greater than 2. And so let's see here. What's the intersection of being greater than or equal to 3 and greater than 2? Well, the intersection of greater than or equal to 3 is more restrictive than greater than 2. So the intersection there is just the probability that x is greater than or equal to 3, divided by the probability that x is greater than 2. And we already know the probability that x is greater than or equal to 3 is 1/4. And so we would just need to know what is the probability that x is greater than 2. So we would integrate from 2 to 4, 1/4 dx. That's 1/4 dx. So this is 1/4 x evaluated from 2 to 4. So this is 1/4, 4 minus 2. And so that's a half. So this is equal to greater than or equal to 3, we know is a quarter. And then the probability that x is greater than 2, that is a half. A quarter divided by a half is equal to a half. A quarter divided by a half is equal to a half. Okay, so we have that. So that's one way to do it, and that's just strictly using the idea of conditional probability getting to that stage right there. Now, an alternative way that we can look at approaching this is to actually just think about what this means maybe in a graphical sense. All right, so given that x is greater than 2, given that x is greater than 2, our distribution then, let me give myself a little bit more space here. Remember, we were originally on the interval from 0 to 4. So we are originally from 0 to 4. So 1, 2, 3, 4. And we originally, our PDF then was originally a quarter. Our PDF was originally a quarter. So we had this here. And we wanted the probability that x is greater than or equal to 3. We did that earlier on. So we were interested in knowing, so here's where this intersects, and we want to be greater than that, so we want to go to the right there, right? So this would basically get cut off right here. So let me just say this. Now, if you're given that x is greater than 2, you can very quickly come up with the conditional distribution by just looking at how this would have to change, in the sense that if we know we are greater than 2, then we have to be to the right of this. So now our distribution doesn't go all the way from 0 to 4, but it only goes from 2 to 4. So what would that density have to be? Well, that has a base 2. That density, in order to integrate to have an area of 1, would have to be a half, right? That would have to be a half. So we've cut our interval in half, our base in half, so our height has doubled from a quarter to a half. So now what's the probability that x is greater than or equal to 3? Well, now it's just this area, which is exactly half of the other area, right? Exactly half of the other area. So you could update this and sort of say that the probability that x is greater than or equal to 3 given x is greater than 2 would be equal to just the integral from 3 to 4 of 1/2 dx. Okay? Either way you want to think about it is just fine, but I do like to tie that graphical interpretation in case you might find that more helpful. All right? Still, nonetheless, it's always good to refresh yourselves on conditional probability definitions, because those will show up, from here on out.